Hi everyone. So yesterday we saw until the linear regression. So today let us see from the linear regression. It is a statistical technique to find the relationship between variables. So in the ML context, this is between we need to find features and labels. So let me pick on a Google document, then we can explain or be more clear. So what we have studied until now, known until now, that in the ML system there are multiple types of learning: supervised, unsupervised, reinforcement, and generative AI. In the supervised kind of a learning, there is a regression, classification. In the classification, there could be a binary classification, multi-class. So we are currently at this. We are at the we are at the linear. So we are at this. So it this they have taken example of a car that let's say okay only wine label is an output and feature is an input, and we need to find the relationship, and we provide correct data set in the supervised learning. We provide data sheet which is labeled, and also we provide correct results for their training so that model could compare and see how close it is to the correct results. So yes. So we have plotted this point. We have plotted this points on a paragraph. Sorry, not paragraph, but a graph. So this left side is the miles per gallon, and this is the label. This is the output that we want. This is the pound in thousand. Comparison between two values. First one is the pounds, and second one is the miles. So it is a car fuel efficiency. It is miles per gallon based on how heavy the car is. It's the weight of the car. So see, these are different points. I will plot a line. This is the best fit line that uh, optimizes or matches most of the dots. And this is the equation: y is equal to mx plus p. Y is the output miles per gallon, that is the fuel efficiency. M is the slope of the line. So this is the slope of the line. X is the pound, our input value, and p is the y intercept. Now we take this exam equation into our ML system. And in the ML system, I explained in the previous video that Y becomes the prediction, the predicting about the output that we want. B becomes the bias, W becomes the weight, and X becomes the value. Now bias and weight is calculated from training. Now what is this training? Training is the uh, period where the model predicts that what is the output. It produces the prediction for this particular feature value and how it predicts. So it takes a random value of bias b and weight, and it takes a random value, calculates the prediction, and now then it matches with the output with the correct results that we have provided in the data set. That I think you will see how it predicts. There are multiple methods like gradient descent, where it gradually descends to a particular line or optimal point where the prediction is most close to the correct result. So here in this, yes. So when we have multiple features, that equation that we use now becomes bounds, displacement. There are multiple features, and again this graph will look like this when we have multiple features. So this graph of for multiple features. What part of linear regression equations are updated during training? We know that is bias and weights. Okay, moving on to the loss. Loss is the difference between the value predicted by the model and the correct result. So it is a numerical metric that describes how wrong the model prediction is. Loss measures the distance between the model's prediction and the actual levels, actual output, and the output predicted by the model. So this is the loss line. Loss line means actual dot line, and this is the output. It could be positive or the negative. So there are two types of, I think, loss: mean absolute error and mean squared error. And what is the difference is that how close we make this choose this is a method of calculation how we close this is to the outlier whole data set. Previous best this is example we okay, calculating the loss. Yes, the MSE mean square error, it means that the model is closer to the outliers but further away from the most of the other data points. We take a sample data points, and if we choose this uh, model trained with MSE, then that model is close to the outliers. Outliers means exceptional cases in a particular data set. And if you choose this loss function, this type of loss, then it is further away from the outliers, but closer to the most of the other data points. In a graphical format, if you see. So this is okay. Let's first read what is the question. Which of the two linear models shown in the preceding plots have higher mean squared error when evaluated on the plotted mean squared? What does mean squared mean? This is closer to the outlier but further away from the most of the data point. So it is closer to the outliers. So model on the okay, the model is close to the outliers but further away from the most of the data points. So the model on the left, no. The model on the right. The six examples on the line incur a total loss of zero. The four examples are not on the line, not very far off from the line. So so it is calculated. How do we calculate the mean squared error? We take each of these data points and square them or take an average for that. Model is closer to the outliers but further away from most of the other data points. That is a okay. So this I misunderstood the question. It's asking both are mean squares, but which plot has the higher mean squared? Which of these two linear models shown in the preceding plots has higher mean squared error when evaluated on the plot? So I both are mean squared error calculated using the mean squared error, but which of these two will have higher mean squared error? So that would be the right because closer to the outliers 1 and 2, and it has more outliers 1, 2, 3, 4. So if you calculate 6 example on the line incur a total loss of zero. The four examples not on the line are not very far off from the line. So the even squaring their offset still yields a low value. So this means it has a higher value. This is a lower value. So this is an interactive exercise with parameters. I'm not studied it, but yes. So this is the weight and bias that I was talking about. We need to adjust the weights. We calculate or see what is the mean squared. Now that should be the minimum or the best optimal possible. And we can adjust the bias and weight and see the where it is the lowest. Now let's adjust the weight. 0 point. Again it starts increasing. So you see 3.7545. I think 3 point, yes, 46. That would should be the lowest. In case of bias, I think again it is 3 point. Yes. So I think yes. Let's see the solution. Solution is the optimal linear model for this data is MSC of 3.37, where the weight is a minus 0.12. Okay, we have put on the 0.12 and the bias of 16.96. Our bias is 16.12. So these are the two interactive exercises. We can adjust the weight slider, and it just shows that how weight and bias are adjusted during training. This is another example. Okay, so this is the answer. Okay, let's move to the gradient descent. So this is the example where it is a okay. First, gradient descent is a technique that iteratively finds the weight and bias that produce the model with the lowest loss. So our goal is producing a value of weight and bias that produces the lowest amount of loss. Now, how it does it selects a random, I think, weight and loss in this model, and again it compares. This is the features, this is data set features and the label. Again, they determine loss. It compares that with the now it determines whether move this weight to the bias and weight to the left side or the right side. Again, move a small amount. Now repeat this loss until loss can't be reduced. So this is a cyclical process. Model convergence and loss curve. Okay, let me answer one of the questions. Yes, what is the question? Loss curve. Okay. What is the role of gradient descent in the linear regression? Gradient descent removes outliers from the data set to help the model make predictions. No. Gradient descent is an iterative process. Yes. I'm not read is convergence and convex functions. I think this is the graph that is shows bias and weight for linear. I have also not read hyperparameters. This I am reading. So once I read this and understand a bit more, so maybe we can discuss. I can share anything that I understand. Okay, that's all. And let me see in the next video what we do it and any questions further this study that we have been doing. Understand a bit better.